Okay. Now you see my tablet?
Yes.
Yes.
Okay. So last week we talked about an order of an element. We said it's the least power that takes it to the neutral element, if there exists such a finite power. Okay, if not, it's just infinite. And now we are going to see one of the fundamental theorems in this area. This is called Lagrange theorem. I mean, it's very natural, I say. Okay, and we will go and see some consequences of this theorem. Okay, so definition. Let G be a group and H a subgroup of G, of course. Then two elements X and Y in G are said to be congruent from the left, or I would say just left congruent. With respect to H. So it's a long name. Okay, if there exists an H in H such that X is equal to YH. We write it, we denote it by this way. Okay, so we say that X is left congruent to Y with respect to H. Okay, if what differs them, okay, I remind you that this is the operation. We don't know the operation, it doesn't matter. Okay, I mean, what differ between X and Y is an element of H, or in other words, X belongs to YH. Okay, what does this mean? Okay, so I know you're not used to this, of course, definition. So let me draw some picture. Suppose this is G. Okay, so this is G. Inside G, we have a subgroup H. Okay. So of course, if we take an element of H and we multiply with respect to the given operation, all elements of H by this little h from the left, then this is going to be just a permutation of H elements, because I mean H is closed. So any output of H with another H is again in H. Okay. So little h is actually H, maybe in another order of the elements, but it's the same set of elements. But if we take an element outside of H, some G, and we multiply all elements in H from the left by this G, then we get another set which we call coset. I mean, these are, I mean, we can also take another element, etc. These are called cosets. Why these are called cosets? Because they are complementary. I mean, altogether, their union is just G. But you can think about this as a shift of H. Okay, so we have different shifts of.
So just to be clear, when you say you multiply an element by a group, you mean multiply each element of the group by that element?
Sorry, again?
The notation is multiplication of an element,
Yes.
lowercase h, for example,
yes,
by a notation of a group, an uppercase.
Yes, this means that you go over any element of H and multiply by this G.
Yeah, okay.
So let me ask you, can these be also subgroups? Can these be also subgroups of G?
Yes.
No, the answer is no, because E belongs only to here. And you cannot be a subgroup if you don't contain E. So these are cosets, but they are not subgroups. They are shifts of a subgroup. Okay, for example, okay. Let us think about, for example, let's take maybe another something little big, U16. So this contains all the numbers that are coprime to 16. For example, we have with respect to the operation of multiplication, because it's order, modulo 16. So it is 1. Actually, it's all odd numbers. So we expect to have 8. Okay, so 1, 3, 5, 7, 9, 11, 12. We don't need these brackets here. Okay, this together with multiplication modulo 16. So this is our G. Now we take a subgroup. Okay. For example, let's take what is generated by 9. So what is it? We have 1, which is E, 9, then 81 modulo 16. How much is it? 81 modulo 16.
Yeah, I think it's 1. No, because
Yes, because you say that
16 times 4 is 64 plus 16, it's 80.
yes, yes. Okay, so okay. So it finished here, isn't it? Now, let us think about the cosets. So we have H, this is one coset. This is it. We're gonna call it the trivial coset. And we have, of course, 3H. 3H is actually 3 and 27, but by 27 is actually 11. You see, this is a shift of this, because this was 1, 9. So I took this 3, I multiplied by 1 and by 9. So I cannot have here the neutral, okay? Because if I had here, so I had an inverse of 3, but 3 doesn't belong to H, so neither is inverse, okay? So this cannot be a subgroup. Let's go further. 5. Now, 45, how much is it modulo 16? Okay, 45, if I remove 13, 13, yes. So this is another coset. And we also have 7. Now 63 how much is?
Okay.
How much?
15.
Did we cover all elements? We have 2 here, 2 other here, 2 other here, and 2 other here. So we have 8, okay. We have 4 cosets. We are going to denote this new set, okay, by this way, G modulo H. Okay, now I'm writing G on the left of H because, I mean, even in this example, it doesn't matter because the whole group is abelian, but in general, it does matter if I multiply this little g by the left or by the right, okay? So if I multiply by the left, I write it G modulo H. This means that these are the residues modulo H, okay? So these 2 elements are the same modulo H. Why? Why 3 is the same as 11 modulo H? Because 3 is equal to 11 multiplied with 9. Now, I didn't compute it, but I guess it has to be. Because there are 2 representatives in the same cosets. Okay. I mean, 3 belongs to this coset. It's the same coset. Okay, it's the same coset. So there must be some H that differs them. And we have only 2 elements in H. It cannot be 1, so it must be 9. Okay, so 99, I guess that 99 modulo 16 is 3. Is it true?
To me, it was a little bit quick. Can you please repeat the last part?
Yes. We are shifting a subgroup by multiplying all the elements of the subgroup with some element of G. Now, if this element of G, okay, is inside H, so the shift is trivial. I mean, maybe the order inside changes, but it's the same contained. But if we take G outside H, for example, this 3 does not belong to H. So if we multiply all elements of H by this 3, we get a shift of H. Now, this element 3 is called congruent to 11. Why? Because these are 2 representative in the same shift. I mean, if we shifted H with 11, we would get the same thing as shifting H by 3. Because 11H is 11 and 99, which is 3. So these are 2 representatives of the same coset. The same is for these and for these, okay? So in other words, modulo H, we get a division of this all G, okay? To, we say these are actually equivalent classes, okay? I mean, if we refer to this relation as an equivalent relation, then these are the equivalent classes, which means that 2 elements are either belong to the same coset. I mean, two cosets cannot have any intersection. I mean, they can be the same or they can be a disjoint. They cannot have in the middle intersection, which is not trivial, but it's not the whole thing. Okay, they cannot have. This is a property of equivalent relation. So I want to show you that this relation, you know what is a יחס שקילות, I mean equivalent relation. Have you heard about it? I mean, it has to be reflexive, symmetric, transitive. You heard about it?
Yeah.
Okay. So we are going to see that this relation, which is defined by this, okay, is an equivalent relation. And we're going to deduce from this that all elements of G are participated to equivalent classes, equivalence classes, okay?
So just to be clear, you mean that all elements of G are, you can divide them,
yes.
You can distribute them to equivalent classes, right?
Yes, exactly. Okay. So, mark. Okay. Why is it true? So first, I remind you, okay, x, y means that x is equal to sum h. Okay. So reflexive complexity. I hope I'm not grammarly, I mean, or writing something in not correctly. Okay. Reflexivity should have written reflexivity. I don't know. Okay. So of course, x is equal to x multiplied with 1, which belongs to h. So x is equivalent to itself. Symmetric. If x is equal to yh, and of course h is invertible, so xh minus 1 is equal to y. I just multiplied the both sides by the inverse of h. So y is equivalent to x. So okay. And transitive, transitivity. Maybe here I should have written symmetry, I don't know. Okay, transitivity, if x is a relation with y and y with z, so this means that x is equal to sum yh1 and y is equal to sum zh2. So x is equal to zh2 h1. So x is in relation with z. Okay. So corollary. Okay. G is a disjoint union of its cosets. Okay. This is how we denote disjoint union with a point inside. Okay.
Yeah, I have a general question.
Yes.
Why are we interested in such H?
Because okay, in mathematics we want to investigate properties of objects. So once we take G modulo H, okay, so we can compare it to other things. I mean, we can say that up to H we know this group, okay, for examples. We're gonna see later. Okay, what I'm saying now, okay, this is gonna be the theorem of Emmy Noether. You know, in Bar Ilan, you have this little room in the Department of Mathematics called after this woman, Emmy Noether. You have heard about?
I didn't.
Okay. So we are going to see it later. Okay, that you actually we want to decompose objects. Okay, so we say that up to something they are like something and etc. Okay.
Cool, thanks.
Okay. So we call this set set, okay, given a group G and subgroup H, okay, G modulo H, which is the set of all cosets. I mean, every element here is a set, is a shift of H. We call this set the quotient. No. The quotient set of G by H from the left. Okay, and these are called left cosets. Okay. So now we can deduce immediately the theorem of Lagrange.
So you don't prove the corollary?
It's
Immediate?
Yes, because this is a property of equivalence relation in general. Once you participate a set to equivalence classes, then the whole set is a disjunct union of the equivalence classes. This is a property of any. I mean, this was the proof actually. Okay, that it is a equivalent relation. Okay.
Cool, thanks.
Okay, Chevron. Lagrange. Let's call it Lagrange theorem. Okay. Given a finite group G and a subgroup H, okay? Of course, the order of H divides the order of G. Now, this is immediate. I'm going to explain why, okay? So this is first now. So we can talk about G divided by the order of H. We call it the index. Okay, this is the index. The index of H in G. Okay, so it's not two things. I mean, it's the same thing actually. Okay. So H, the order of H divides the order of G. So we call the quotient, the ratio, the index of H in G. Okay. Now, why do I say that this is immediate? Because of course, by the way, okay, of course, this is also the order of the so this is the number of cosets, of course. Why this is all the same thing? Why? Because to any G, GH is the same order of H. Okay. By the way, you cannot have here two elements that appears, I mean, one element that appeared twice. Why? Because, okay, if G1, if G with some H1 is equal to G with some H2, then of course you can multiply both sides with G minus 1, and it means that H is equal to H2. So you don't have a repetition here. Okay. And of course, the cardinality is the same because it's the same number of elements, just shifted. So if we have this thing, this property, and we also know that G is a distant union of its coset, okay? So it means, okay, that the order of G, if sigma of H, and how many times we take it? The number of cosets, okay? Okay, so we don't need this is exactly what it means, that you can pave your floor by shifts of one size H, and a shift of H, and a shift of H. How many shifts? The number of cosets. Okay, and we call it the index. Okay. So one immediate consequence is that any element in G, its order divides the order of G. Why? Why is it true? Why do I say that any element of G, its order must divide the order of G? Because the order of an element is the number of elements in the group that it generates. You remember that? Okay, the order means that how many powers you have, distinct powers you have until you get back to E. Okay? So this is a subgroup. And Lagrange tells us that any subgroup, its order divides the order of all G. So any element, its order divides the order of the group. It must be. Okay? And if you remember, I told you that I'm going to get to this when we talked about the classification of cyclic groups. In the proof there, I told you that I'm going to show you, okay, that that if we take, okay, so always you take an element of G. In the power of G, this must be E. Because it is G, the order of G, with some Q. So it is E. Okay? And together, this is G. Okay?
Why did you took G to the power of order of G because this is E? And
I'm just showing you because if you remember this, let me take you a moment in the proof that we have seen classification of cyclic groups. I told you we will show that the order of an element divides the order of G. It was here that we needed that. Here we started by an element, a group of order n, and we said this must be E. Okay, so now we understand why it must be E, because if n is the element of the whole group, the order of the whole group, so any A is E in the power of n. Okay. Now, the same can be said, okay, similarly, okay, we have the quotient set from the right. We write it in this way. These are right cosets. Okay. Okay. Now, if G is abelian, so of course it's the same thing. But anyway, Lagrange theorem talks about both things. I mean, it doesn't matter. because, okay, let us see examples, okay? Let us see examples. I mean, the proof of Lagrange, I mean, it's exactly the same with this thing also, okay? So we can write it in Lagrange. This is also equal to G modulo H. This is the same, okay? Okay, for example, you can take a map taking an element, a left coset to a right coset, and prove it is injective. Okay. So, okay, let us see examples. Maybe I want to tell you another thing because before we see examples. Okay, let us see examples. So the most common example is actually what we denote by Zn. Zn, which we call it the group of remainders modulo n, it exactly Z modulo nz. It's the same thing. Because if we take Z modulo 3z, so what is this quotient set? These are shifts of this subgroup. Now, you see here, both are infinite, but the index is finite, okay? The index is the number of cosets, is finite here. I mean, you can also have index infinite in general, but here the index is finite. What are the elements of the cosets here? What are the cosets here? So you have the trivial coset, which is 3z. You see, this is our h, and this is our g. Then we have 1 plus 3z, and we have 2 plus 3z. That's all. I mean, if we go further, 3 plus 3z is again 3z. So this is how we should have maybe defined this group in the beginning, but we didn't want to enter this notion at this early stage. But this is how we define this ZN. Okay, it's the group of remainders, or if you think this group of shifts. Okay, this is one example. Let us see an example in which the left cosets are not equal to the right ones. Okay, think of G as GL2Z2. This is the smallest group which is not abelian. We have 6 elements. Of course, it's multiplication, and inside this is always modulo 2. Okay. By the way, you cannot generate this group by a single generator. How do we know it immediately? That you cannot generate this group by a single generator. How do I know it without computing? Because if it had been true, so this group was cyclic, so what it was abelian, but it's not abelian. Okay, so you must have at least 2 generators, because we have seen that any cyclic group must be abelian. So it's not abelian, so it cannot be cyclic. Okay. Now think of this subgroup being generated by this element. This subgroup contains only 2 elements, the E and this one, because if you take the square of it, you get back to E. That's all. Now let us think of G modulo H from the left. Okay, so you have H. Let us think of this. This contains, I multiply this by these 2 from the left. So you have this element and you have also this, which is some reflection. This is 0, 1, then 1, 0, then 0, 1, and here it must be 0, 0, 0. Okay. And remember, okay, remember that the number of cosets, this is Lagrange. The number of cosets is this one. And it doesn't matter if from the left or from the right. This is what we call the index. Okay, so in the first example, the index of 3z in Z was 3. We had 3 cosets. Now this is 1 coset. Here we expect the index to be 6 divided by 2, 3 cosets. So this is 1 trivial coset. This is another left coset. And now we take an element that does not belong either to this or this. For example, what we can take this one. And get, and what more? Zero, 0, and 1, 0, 0, 1, and 1. So we have 3 cosets. We have this one, we have this one, and we have this one. Is it clear? If something not clear, please tell me. These are three left cosets. Why left? Because I multiply from the little g from the left. Now let us compute it from the right. So we have h. We have h multiplied with this, which, of course, if you multiply this element with e, it's the same element. But now, if I multiply this with our generator, I get 0, 0, 0, 1, 1, 0, 1. Okay? And what do I see? I see an element here that wasn't here. I don't have this element. Let me color it in another way. Oi. We didn't have these cosets before. Just a minute, just a minute, just a minute, just a minute. Why do I, okay, yes, of course, it's okay. So here it must be like this, and what can be left? We have something here left. I mean, we are missed this one. So it must be this one. Okay. So you see, of course, H must be in both. But you don't have this coset here. Okay, and you don't have this coset here. Okay, so actually, you see that G modulo H is not equal to G modulo H. Okay, these are not the same elements. But of course, the cardinality is the same, is 3. Because you needed the same numbers of pavement to pave the old floor. Okay, because it's a 6 modulo 2. Okay. So one very important consequence that we are, I mean, this is the basis of cryptography, okay, is the following one. So now we call it the Euler theorem. Now, of course, other in his period of lifetime didn't call it groups. I mean, it's a formulation of his result in a new language, okay? So in this new language, what Euler says is the following thing. And we are going to see that this is the basic theorem of what we call today RSA, okay, in cryptography. It says that to any two natural numbers, if they are coprimes, okay, then A in the power of Phi is 1 modulo n. Okay, and the proof is immediate. Because if A and N are coprimes, then A as a representative of a class belongs to the Euler group, which means that it is invertible with respect to the multiplication modulo n. So it belongs to UN. So A in the power of the Euler group order, remember we've just seen that any element in the order of the Euler group is 1. But 1 means 1 modulo n because we are in UN. Okay.
Can you please remind me what is A bar?
A bar is the I mean, originally the elements in UN, I mean, any element is infinite numbers. So when we say A bar, we mean the class of infinite numbers, all of them with the same remainder modulo n.
Cool. Yeah.
So little n is a representative in this infinite set. Okay, example. Okay, what are the 2 last digits in 9 in the power of 121? Of course, it's a great number. Okay. Solution. So we actually want to compute this number modulo 100 because we are only concerned with the 2 least significant digits. So we don't care about the other digits. We only want to find the remainder modulo 100. Okay, so we say that 9 is coprime to 100.
Yeah, 1 second. I didn't understand. 9 to the power of what exactly?
1 to 1, 121.
Ah, okay. It's not a pipe or something like that. Okay.
Yes, maybe it's like a absolute value of 2.
Okay.
So we know that 9 is co-prime to 100. So by order, 9 in the power of, what is phi of 100? So it's phi of 4 multiplied with 25. These are co-prime, so we can split them. So it's 4, 1, 2. So it's 2 times 20, it's 40. We have 40 elements in U100. So 9 in the power of 14 or 40, okay, is 1. This is Euler, you see? So I want to understand what is this thing. So 9 in 1 is 1 in 14. This is 120. Multiply 2. So this is all 1. So the consequence so the two digits are 0, 9. Okay. Okay, the two digits are okay. Now you have heard about Fermat. Okay, so this is another theorem, not the famous one. So we call it the little theorem of Fermat.
I'm sorry, what do you mean by the two digits of 0, 9?
I mean, you take this large number and you take the least significant two digits.
Okay. Yeah, I forgot the question. Okay.
Yes,
Yeah.
it finishes by 0, 9.
Yeah, okay.
Of course, it's a very great number. It's a very big number. Okay. So my little theorem says that if you have if 3 is a prime number, okay, not dividing some a in n, then a in the power of p minus 1 is congruent to 1 modulo p. What is the relation between Fermat theorem and the other one? Okay, so I took here a prime number p, which does not divide a. Of course, a does not divide p. Okay? Because p is a prime and a is not equal to p. So actually, p and a are co-primes. So what is the relation between Fermat theorem and the other one? What do you say?
Yeah, you get exactly that by assignment, right? You can take n to be p, and
it's just a particular case of Euler, isn't it? I mean, Euler is more general. If you take your n to be prime, then of course phi of n is p minus 1, and that's all. So tell me, okay, so what? So Fermat wants to find a particular case. This is a Fermat, is important mathematician. So what
before it.
What?
It was before the Euler theorem.
It was before, exactly. Okay. It's like, you know, Maclaurin Taylor. So Maclaurin put 0. Okay. No, Maclaurin, this is what interesting. Taylor just generalize it, okay? And etc. Okay. Definition. Okay. Let G be a group and H a subgroup. Okay. If G modulo H is equal to G modulo H from the right, I mean, they are the coset, the left coset are equal to the right cosets, then we say that H is a normal subgroup. Okay, and denote it in this way. H, this triangular. Okay, so H is a normal subgroup. Of course, if G is abelian, so any subgroup is a normal subgroup. Okay. For example, so I'm not taking an abelian example because it's not so interesting. Okay. If the index of G inside of H inside G is 2, then H is a normal subgroup of G. It must be. Why? Because the left cosets can be H and what?
Another element from G that multiplies H. So
yes, but the all, I mean, the union of the cosets cover G. So what, right. We have only 2 cosets.
Yeah.
So what can be the other coset? The complementary. I mean, you don't have another choice. Okay. And it is exactly the same. Okay. For example, if G is our GL2Z2 and H, now I'm going to take H not of order 2, because of order 2, the index was 3. Let me take H of order 3. Then the index must be by Lagrange 2. Okay. For example, if I take this group, Okay, so I leave it to you to show that this is a normal subgroup. Okay, it's a normal subgroup because the index of H will be the order of G. This is Lagrange. Okay, which is 6 modulo 3, it's 2. And why is 3? Because the order of this subgroup is 3. Okay, it's square, it's not the E. I mean, you need 3 stations to get to back to E. Okay, I mean 2 other stations. Okay, why do we need this property of being normal? The answer is another definition. Okay, I know that we see a lot of theory. We're gonna see after that examples, and by Emmy Noether, we're gonna see how all mathematics can be, all algebra can be rephrased in this way. Okay. I mean, you cannot write today a paper in algebra without using Emmy Noether theorem that we are going to get next time, maybe. Okay. So these are very important things. These are a basic of what we call modern algebra. Okay. So definition. Given is a normal subgroup G, okay, the quotient group, so now we don't call it quotient set, we call it quotient group. Contains, now it doesn't mean it doesn't matter if it's a left or right. Until now, I didn't say anything new. This is also the quotient set, but now I give an operation that makes it a group, okay? With the operation.
How can it be a group? The neutral element isn't there.
No, the neutral element will be H, will be the trivial shift. It's a new group.
Okay, got it. Yeah.
Okay. If we take 2 elements, okay, so the operation between 2 elements is exactly the original operation. Only we know that this thing is equal to this. Okay, so we enter this, we multiply it by this, and we got a new element in the quotient, which is this. And it is well defined because HG2 is exactly like G2H. These are the same because it's normal. So you actually multiply the two representatives. And this is going to be the representative of the new coset. Okay, this is the quotient group. Okay, example. Okay, so of course, Z modulo NZ, which we call it Zn, okay, is a group. Up. For example, Z modulo 3, Z, what we call Z3. We have Z, which is our neutral element. We have, sorry, 3Z. 3Z is the neutral element. We have 1 plus 3Z, and we have 2 plus 3Z. Now, if we want to make an operation between this and this, we actually get back to 3Z because this plus 2 is 3. So this is the inverse of this element. Okay, because this is our neutral.
I have a question.
Yes. Oh.
The coset, every coset will be a subgroup of G?
The only coset which will be a subgroup of G is the neutral, is the trivial shift. I mean, it's the subgroup. Any other coset cannot be subgroup because it does not contain. I mean, it cannot be considered. I mean, if you think of this as a subset of Z, so it's not a subgroup. But now we are in a different world. In this world, these are elements in the new group. This group contains only 3 elements. And our new E, it's a new E. It's not the E from Z, because the E in Z was 0, that's all. The new E in this group is this subgroup. Okay, let us see another example. Okay, think of G as GL. I want to show you. Okay, so believe me for now, and I will show it later. Okay, we have this group, okay, with all matrices n square with a real interest, and we take its subgroup SLN. Of course, this is not an abelian group, but still this SLN, okay, is a normal subgroup, though of infinite index. So I'm going to show you later why is it normal. But for now, let us think of G modulo H. This is, since it's normal, we can think of it as a group. So what will this contain? So we have SLN.
No.
Say
No,
it, say it.
No,
Any
no, 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 no.
cosets, it's the all matrices with the same determinant.
Yeah,
Yeah,
okay.
exactly.
But it seems, yeah, infinite to me. It was a little bit
Yes,
strange.
yes. Okay. You cannot describe it as before because you have, okay. We are going to show later by Emmy Noether that this is isomorphic to this group. Any invertible element here corresponds to one coset here. So this modulo this is like the all numbers, without zero.
Yeah, so the order is basically Aleph, right?
Yes, yes, yes.
Yeah.
I wouldn't say Aleph. Yes, Aleph without the zero. Yes.
Yeah.
Yes, yes, yes. Okay. So I will write it. Okay. Now, why is it normal? I have some minutes, okay? A remark. In order to show that H is a normal subgroup of G, we can show that to any G of G, G, H, G minus 1 is equal to H. Why? Because this is the same thing as saying, okay, that GH is equal to HG. So, an example. Let us take the previous one. Take G to be GLN. Okay. And take H to be SLN. SLN means all matrices with determinant 1. So if you take an element H, okay, and this, by the way, this is the same thing as always saying, okay, that G, H, G minus 1 belongs to H. It's the same thing. Any conjugation of an element H by an element G remains in H. It's the same thing. Okay, so if you take an element H, a matrix from here, and you multiply it by an element, a general element of, not this, this way, G, an element of G, of any determinant not 0. Okay, and you multiply it by a matrix here and by its inverse. What will be the determinant here? Will be what?
1 second. I think that it's homomorphic, right? Determinant. So you can take determinant of each element now, or am I mistaken?
No, you're not mistaken. It's actually
yeah.
Which these are reduced, and this is 1. So any G, yes, here is for any H. So any G and any H, okay, G, H, G minus 1 belongs to H. This is a matrix with determinant 1, okay? So this is exactly like saying H is a normal swirl group in G. In general, not only here, okay? Do you have any questions? So how did I know this correspondence? Okay. So of course, the correspondence is given by coset here goes to what? What do you think the correspondence will be? A coset here goes to what here? What do you think? H is SLN and G is GLN. We take an element of G and we shift all SLN. So what?
The determinant of G times H, of G times the element in H.
Of G, that's all.
Yeah, okay.
Okay. So this is one example of what we are going to see next time. Amy Noether, first isomorphism theorem. She has 3. Okay, she's a great woman. Okay, you cannot not admiring her. Okay, so we are going to stop here. So don't be afraid, okay? We are going to see these things over and over. So finally, I hope this will be understood. Thank you for listening.
Thank you.
Thank you. Can I ask you one quick question?
Yes, of course, of course.
When you finish the recording?
Okay.